Yeah, but I think it's not the radius of the atom, but like see most papers on nanomechanics, that's what your question is about. They use linear elasticity. The challenging part is, which they don't say anything about, is do the predictions from experiments agree with the computed or numerical results. That's where the challenge is. So, I mean, I do not know. I mean, like why journals are willing to publish those papers. Because as you said, like linear elasticity or even nonlinear elasticity may not should not apply, but they don't require that the results be, is it working? Yeah. That the results be compared with experimental observations. So same thing is like what is the thickness of a single wall carbon nanotube? What is the yeah, you are expert in that, or you, at least your advisor is. So what is the thickness? What should we take for the thickness of a single wall carbon nanotube?
3.4.
From where did we get it?
Literature.
Huh? I know, but from no, that you cannot say you got it from the literature, because you are a scientist now. You are supposed to tell me how did you get it. Like on what basis do we say that the thickness of a single wall carbon nanotube or a single layer graphene sheet is 3.4 nanometers? You know my question? I know that 90% or 95% people, maybe more than 95% people use the value just said. And the basis for that value, or one basis for that value, is that if you take a multi-wall carbon nanotube or a multi-layer graphene sheet, then the distance between adjacent walls of a carbon nanotube, like double wall or triple wall or 4 walls, is 3.4 nanometers. But that does not mean if I take a single wall carbon nanotube and do either say MD simulations, molecular mechanics simulations, or shell theory or whatever, and derive its Young's modulus, and then make a composite, or even if you don't make a composite, say you test a single wall carbon nanotube in using an atomic force microscope, that the results, experimental results, will agree with the predictions. Most likely they don't agree. I think there is a 90%, 99% probability of not agreeing. I know they use a 3.4. You were very quick in responding yes. So I think that's a touchy question. I mean a few of us have used other ways to find the thickness of a carbon nanotube or a graphene sheet, a single layer graphene sheet, and we don't get 3.4 nanometers. But that doesn't mean that our result is correct, because we derived that based on some other assumptions. So our assumptions may not be good. Okay, so as we have been saying, unless you make assumptions, you don't get anything. Like you say these balance laws hold, well, these are assumptions, right? And the reason they are reasonable or they are good is because predictions from them, these balance laws or continuum theories or linear elasticity theory, these predictions from them agree with the experimental results quite well. And the one I was talking about was the membrane problem. I'm going to do that now, that indeed you will get two solutions. That linear elasticity does not predict. So therefore, you have to change, you have to improve upon your theory. And not every stress strain law, even if you have used nonlinear elasticity, not every stress strain law will predict it. Okay, so I will start with that one. Anything else you want to say or ask? But today is our last day, right? Oh, before I forget, in the afternoon we will start at 2 o'clock, because some of you have flights leaving late in the evening, and drive from here to Calcutta is at least 2.5 to 3 hours. So we will start at 2 and end at 4. So that really means you have a little shorter, well, 1 hour shorter lunch break. Okay, anything else on your mind? So let's do that membrane problem. So we take a rectangular membrane, and so thickness here is very small as compared to the sides, and we say this is x1, x2, and x3, and this is made of a monorevelant material. I think that will so it's monorevelant material, and that means that Cauchy stress is minus P delta Ij plus C1 Bij plus C2 B inverse Ij. So we derived, well, yes, we derived that yesterday, where C1 and C2 are constants. So we are going to follow an inverse approach. What is given here on these surfaces is T I tilde, like on this surface the outward normal is 1. So T11 is given to be, say, P over undeformed area, or let's say is given to be, this is, we have already computed P over A0, and so this is a stress P delta I1. So that's the normal load on x1 equal to L. Lx, and of course 0 also at the other end. And on the Ti2 is also given to be P delta I2 on x2 equal to Ly and 0. So this distance here is Ly for L2. And the top and the bottom surfaces, so Ti3 is 0 on x3 equal to 0 and h, where h is the height or thickness. So we have the stress strain law, and we have the equilibrium equations, and I'm going to use Cauchy stress. So we have the equilibrium equations to be satisfied. So that's the problem definition basically. We are given the material, we are given the loads, We are given the initial shape, find the deformed shape of the body. So, what we are going to find is, and I am giving you the answer beforehand, that there are two deformed shapes. So, depending upon the load P, for some values of load we will get one solution which we expect, in which case the stretch along x and y axis or x1 and x2 axis is same, and for at a certain value of the load the solution will bifurcate into one where the two stretches are not equal. That one, the solution in which the two stretches are not equal, is stable. So, the approach being followed is inverse approach. So, we assume that x1 equals say alpha times big X1, x2 equal to beta times big X2, and x3 equal to gamma times big X3. So, alpha, beta and gamma are the stretches along x, y and z axis, or x1, x2 and x3 axis. Material is incompressible, therefore, alpha, beta, gamma must be 1. So, that will help determining the hydrostatic pressure. Also, if we write T, so that is minus P times identity plus C1 B, when F in this case is trivial, is alpha, is a diagonal matrix alpha, beta, gamma. I think we did that yesterday also for the tension problem. So, it is the same, and so this will be then alpha square, beta square, gamma square, and plus C2 B inverse again is trivial. So, that is 1 over alpha square, 1 over beta square, 1 over gamma square. Now, if we use the equilibrium equations, so that will give us minus delta P over delta xi is 0, because alpha, when you satisfy this one, T11 comma 1 plus T12 comma 2 plus T13 comma 3, T12 is 0, T13 is 0. So, really you have T11 comma 1, and alpha square is constant, C1 is constant, C2 is constant, this is constant. So, only thing you get is delta P over delta x1 should be equal to 0, and then you get delta P over delta x2 should be 0 and delta P over delta x3 should be 0. So, this one says P is a constant, so that is like P 0, same we had yesterday. And now, if we satisfy the boundary condition on the top and the bottom surfaces, is Ti3, even though I wrote here tilde, but Ti3 Cauchy stress is also 0 on the top and the bottom surfaces. So, well, let me, anyway I have to write Cauchy stress. So, T is J, T tilde, oh no, yeah, T tilde, T tilde is J T F inverse transpose. J is 1, so I do not need to worry about it. So, this is T11, 22, 333, so T33, and F inverse transpose is 1 over alpha, 1 over beta, 1 over gamma. So, it is trivial to find T tilde, right. It is a very simple problem. So, therefore, if T33 tilde is 0, that is what this boundary condition is, and all these stresses are constant. So, it does not matter where on which surface you find, and that will give us P0 minus P0 plus T33, which is C1 B33 gamma square plus C2 over gamma square, and this is 1 over gamma, so that should be 0. So, that takes care of this this boundary condition, and that since gamma is not equal to 0 or infinity, so I can get rid of this. So, that determines P0. So, P0 equals C1 gamma square, but gamma from here is 1 over alpha square beta square plus C2 alpha square beta square. Because gamma is 1 over alpha beta, so is it okay? So, now let us use this boundary condition. So, what does this boundary condition say? Of course, that says T11 equal tilde equal to P, T22 tilde equal to P. So, that means T11 tilde should equal T22 tilde. So, let us do that, and so I am going to erase this part. So, T11 tilde is 1 over alpha minus P0 plus C1 alpha square plus C2 over alpha square. So, that is T11 tilde. First term P is P0, C1 alpha square, C2 over alpha square should equal 1 over beta minus P0 plus C1 beta square plus C2 over beta square. Is it fine? So, now let us substitute for this. P0 is this quantity. So, we will have 1 over alpha. I am debating, can I, before I substitute, maybe I can simplify a little bit. So, let us take P0 the terms on the left side or right side, say let us say we have C1 alpha minus beta. This is C1 alpha, alpha square over alpha, beta square over beta plus C2 1 over alpha cube minus 1 over beta cube, C2 alpha cube beta cube. So, should equal or say minus P0 1 over alpha minus 1 over beta is 0. Right? So, as you can see, alpha minus beta is here. This will be beta cube minus alpha cube. So, beta minus alpha will be a common factor. Here also beta minus alpha will be a common factor. So, one solution clearly is alpha equal to beta. So, I am going to now erase this part because I need P0. So, alpha minus beta is a common factor. So, this term is C1 plus, so it will be minus C2 alpha square plus beta square plus alpha beta. It's minus because this is beta cube minus alpha cube. Okay, so this one will be beta minus alpha. So again, plus 1 over alpha beta, and P0 is this quantity, which is C1 over alpha square beta square plus C2 gamma over. This is alpha square because this was 1 over gamma square. So I wrote wrong. So that's alpha square beta square equal to 0. Yes. I'm sorry. This one. See, it's beta cube minus alpha cube. If you factor it, it's beta minus alpha multiplied with beta square plus alpha beta. So that's what I wrote. Oh, denominator. Okay. Thank you. Yeah. Alpha cube, beta cube. Yeah, thank you. Okay. So now let's multiply with alpha cube, beta cube, because just simplification, nothing will change. So it's alpha minus beta, and also let's divide by C2 or C1, whichever you like. So let's divide, because this is C1, C2, C1, C2, so we may as well divide by one of the two. And I have no preference, so let's divide by say C1. So this will be 1, and we are multiplying by alpha cube, beta cube. So that's alpha cube, beta cube. And this term is C1, and that will be 1. Because we are multiplying by alpha cube, beta cube. So that will be just C1 here left. Good. So plus C2 over C1, because we divided by C1. And what do we have? Let me write minus, because otherwise I have to put too many minus signs. So minus, so this will be alpha square plus beta square plus alpha beta, and this will be alpha 4 beta 4. So if C2 is 0, then we have Mooney material. Okay. If C2 is 0, then we have a Mooney material. Then you are keeping only first term in the Taylor series IB minus 3. So if we have a Mooney material and C2 is 0, what solution do we get? There is only one solution, alpha equal to beta, right? Because if C2 is 0, this term cannot be 0. is alpha is a stretch between 0 and infinity. So, this cannot be 0, therefore, only solution must be alpha equal to beta, and that is what Kearsley. Oh, beta is stretch, beta is stretch. It has to be between 0 and infinity, right. So, if C2 is 0, there is only one solution, and that is what Kearsley he considered more general material than the one we are considering. He did not consider Mooney-Rivlin. Actually, he worked in terms of the stored energy density function W, and he showed that if this ratio is 0, which amounts to saying that we have a Mooney material. So, for a Mooney rubber, there is only one solution, alpha equal to beta. So, you pull it, you will always get a square deforming into a square. On the other hand, if C2 is not equal to 0, now C2 over C1 are generally, C2 and C1 are of opposite signs. They are not, this one does not indicate that, but if you do experiments, you do get C1 and C2 of different signs. So, this term is positive. Okay. This is the one that is causing headache in a way. See, that is alpha 4 beta 4. So, let me first say this is positive, because this one is of opposite signs from C1. So, as you keep on increasing the load, which means you are increasing alpha and beta, for a while this term equal to 0 gives you a solution. After a certain while, this term gives you the solution from the second term has lower potential energy and is therefore stable. So, so it switches. Now, let me see if I can show you that. Oh, so you will see it on this TV? Yeah. Okay, this is the experiment. Well, the setup is this. You have a rubber membrane, and basically, as I mentioned yesterday, you are applying loads via pulleys. So, you are applying dead loads. So, initially these squares they are deformed into squares, and when we reach the critical load or the critical stretch, actually it's a loading problem, it's not a displacement control problem. It's not a displacement control problem, it's a load controlled problem. So, you can I hope you can see it, that these are no longer squares, they become rectangles. And at least for me, I do not know from here, but on that one I can see clearly. So, the top picture is like undistorted reference configuration, and this is a supercritical configuration. And you have, if you cannot see it here, then it's on the internet. So, you can, if you go to my web page, then you can download this, well, either download it or see it, whatever you like. Is in 2005. So the publications there are in terms of decades. So if you look at 2000 to 2009 and then search for either Muller or membrane, you will get this. So this is what we were talking about. So this is lambda 1, lambda 2, instead of alpha and beta it says lambda 1, lambda 2. So initially this branch is stable. You are getting, of course, if you plug in the values of C2 and C1, you get alpha equal to beta, and then you solve this. So you are getting unequal roots, which is okay. So at this point, where do the two curves intersect? You set alpha equal to beta in this equation. So when you set alpha equal to beta in this equation, then you will get the point of intersection of the two curves. So one is straight line alpha equal to beta, the other is this hyperbola, and wherever they intersect, so that's this point. The loads you see here, these are in I think grams from tree loads experiments. I think I mentioned yesterday tree load. So these are from experiments, experimental loads. If you predict, like if you plug in the values of C2 and C1, first let me show you that those values of these constant C1 and C2, like I was saying, they are of opposite sides, sorry, opposite signs, and the values here you see is S minus 1. S minus 1 is analog of C2, is 251 grams per centimeter squared. So these are kind of strange units, rather than saying megapascals or kilopascals. This is grams per centimeter square. And S plus is C1. So that's 2010 grams per centimeter square for the rubber that was tested. And so indeed C2 and C1 are of opposite signs. And if you predict the point of instability, that comes out to be this load at a stretch of 2.84. The load comes out to be 1125 grams, and you can see that the two curves intersect at 1125 grams. I mean, it's really getting very lucky that we get right on the money, but even if it were say 1130 or 1120 or even 1110, that's reasonably good. So what it says is that besides the test we did yesterday, where we plotted y versus x, which was y was not quite the axial stress, but it was we did the Rivlin plot, and I said if your data does not fall on the Rivlin plot, then it cannot be a Mooney-Rivlin material. Now supposing it did fall on the straight line, you found the values of C1 and C2, then you can do this test. I mean, this test is not trivial, so you have to be careful when you set up the experiment. So if you do this test and indeed the instability occurs at the predicted load or predicted stretch, you have now a verification that the material you are using or testing is Mooney-Rivlin. So please do not trust with one, like if you do a simple tension test and do the Mooney plot and you get the values of C1, C2, if I were you, I will not say my material is Mooney-Rivlin unless I do some other test. So this is again similar to the simple tension test, right.
All these points are dots are experimental data,
Yes, those loads you see, those are experimental loads, right.
and those continuous lines are theoretical.
Yes, it's it's remarkable that in this case the agreement is great. Okay, this is, I mean, again also these experiments, as far as I can remember, this is not sorry, this is not our data. I think this is probably see, this is Treloar's data. So the Treloar's, when he did experiments, he had some curves like this, these ones. So people interpreted that result as saying that Treloar observed bifurcation. He did not, because the loads he used, they only go up to like say 500, and the instability occurs at 1125 grams. So he did not observe instability. Okay, I mean, I'm not saying Treloar's work was not good. It was excellent piece of work. He's a pioneer in rubber elasticity. The interpretation of his experimental data by people like you and I was not correct. His data is correct. He says in his paper very well that the unequal stretches I observe are probably because of the anisotropy induced in the material due to deformation or some kind of inhomogeneity, and then he averages the two stretches. He says, I am going to take lambda 1 plus lambda 2 over 2 and plot load versus that, because loads are equal. So he said, no, my stretches are not lambda 1 or lambda 2, it's the average of the two. So the point we were trying to make is that Treloar did not stretch his rubber to the load where the instability occurs. On the other hand, if you take a Mooney material, which means C2 is 0, then you will not get instability. So if you test your rubber before using it, and indeed you see this kind of instability, then you are sure it's not a Mooney material. And if your stretches at which instability occurs is very close to the predicted value, then you can say yes, it most likely is, or it behaves like a Mooney Rivlin material. Okay, so it's in some ways it's a negative result. Like we were mentioning before also, that if to disprove something you need one counterexample, but to prove something you need lots of example problems in which this is true. You need to consider many cases. So if we consider simple tension test and biaxial stretching, I mean that's not enough, but still it's better than having only one. Okay, yes, go ahead.
So I was thinking that if this is load controlled and you have a similar setup for a circular member, it can be done, right? If it is not displacement controlled.
No, if it is displacement controlled, you will not see instability, because in the displacement controlled you are stretching it by equal amounts.
Yes.
Then how will I see that lambda 1 is not equal to lambda 2?
But just for the experimental setup, it can be then done, right? For the circular.
Because circular, yes, it can be done, yeah. But what I will see, I don't know. But see, problem is, no, I was thinking about your suggestion, which is an excellent one. The problem is, one problem is that which two stretches I will be considering, radial and circumferential, right? First of all, I don't know if radial and circumferential should be same. and if they are not required to be same, because one is u over r, the other is delta u over delta r in linear work. So, if they are not required to be same for equal loads applied, then how will I see that instability has occurred?
So track the shape.
Track the shape. Yeah, it's possible that a circle will no longer remain a circle. We'll try it. Sure. Okay. Anything you want to ask about this? Go ahead. Then I'm going to do the torsion problem, and I'm going to show you that for the torsion problem, the length will change. I cannot tell you beforehand whether the length will increase or decrease, but it will change. And the change in length, I will show you that. The change in length is proportional to the angle of twist square, or the square of the angle of twist per unit length. So, if the square of the angle of twist per unit length is small, then you really need precision equipment or instruments to detect that, because if the length changes by say 1 millimeter, so you are say 1 millimeter, then you should be able to see that. So, that means unless your instruments are sensitive enough to detect that, you will not see it. Also, you will see when I derive the expression, I am debating whether because I cannot complete it in 10 minutes. So, either we have earlier tea break or whatever, or we have a later one, or you ask any other question you like and we can discuss that.
It should decrease, right?
I am sorry?
The length should decrease. The length should decrease in torsion.
No, it will depend upon the sign of C1 and C2. No, it will depend upon the signs of C1, I think C1 plus C2. So, I can, in our case, because we took both positive signs, it will come out to be I think C1 minus C2. So, it will depend upon the signs of these. So, unless you tell me C1 has this value and C2 has that value, give me the signs, I won't be able to tell you whether it will increase or decrease. All I can tell, well, all the theory predicts, it's not me telling you, all the theory predicts is it will change. So, that's roughly speaking Poynting's effect.
The length will change, right?
The length will change.
And this is for a circular cylinder.
Is for a circular cylinder, right?
So, will it be wrong to say that for this kind of a material we observe some sort of effect equivalent to warping even for a circular cylinder?
Yes, it's wrong to say that, because warping refers to the material in different sections of a circular bar. Like this material is coming out of the chalkboard and this one is going into the chalkboard. But in our case, we are going to assume that plane sections remain plane and still the length will change. So, so it's not quite like warping, and generally this warping occurs if you have a non-circular cross section, yeah, whereas we will consider a circular cross section. One reason we are going to consider circular is it's easier to do the algebra. It's not a, there is no magic, but it's easier to do the algebra. So the intention is to do the torsion problem and then do the radial expansion of a tube, but there what we want to do is we want to show you that you can invert the tube, you can pull it inside out. Okay. So, if I can do that in my with my arteries, so if my artery is say clogged and they know where it is clogged. Incidentally, I was reading in the newspaper today that somebody got angiogram done in Calcutta a week ago, and they did not find any artery clogged, but during the procedure the artery got torn up, so the person died. Even though it's a routine procedure, I mean seriously, it's a routine procedure, because doctors like cardiologists do this probably 50 a day. So, but it's a matter of luck, you know, you never know. When we say it's routine, that doesn't mean the success rate is 100%, and even if it is 99.9%, so there is still 0.1% chance. So anyway, what I was going to say is that supposing it were clogged, and then I can pull it inside out, I can clean the outer surface, put it back in. So then I don't have to take a vein from my leg and put it there. So it's, I mean, it has some practical use, but for us it's a mathematical interest to see that indeed this nonlinear elasticity theory predicts two solutions that I said it should predict. Again, when I say I said, I'm really repeating other people's work, it's not my work.
So is the pointing effect kind of complementary, using it for lack of a better word? Like you're twisting it, you're finding a length increase. So
Right.
if you try to increase the length, does it twist?
No. No, if you do a simple tension test, the bar does not twist. No. See, like we did yesterday simple tension test, nothing happened about the twist part. Yeah. No, it's not reversible, like they are not complementary to each other. If you twist it, it elongates, assuming of course you don't apply any loads. I mean, so what will happen is if you twist it and you are compressing it or stretching it, then you can have the length not changing. But when Poynting did this experiment like almost 200 years ago, he had 10-meter long wire hung from a tree, and he could see it. See, this is innovative experiments, right? He had an idea, yeah, it's going to elongate. Now he wants to show experimentally it does. I mean, when I say elongate, it could have been changing, like contracting also. But in his case, I think the wire elongated. And so the instruments were not sophisticated enough to see with the naked eye is going to elongate or not. So he took 10-meter long wire. When I say 10, don't take me literally, but yeah, he took a very long wire, so he could see it. So that's what we will do after the maybe after the break. So we will do that torsion problem, and then if we have time, we will do the radial expansion of a tube. And I promise I will do bending of a beam. So we will do that too. So I think these 4 problems probably we can do today. Okay, so let's have the coffee, even though it may not be ready yet. I don't know because it's supposed to be at 10:50. Okay, we can check. Composites. Okay, so the goal is now to derive the strain energy density function, stored energy density function for a fiber reinforced material. Yesterday we did for an isotropic material. So for an isotropic material, I think we talked about how to cut specimens in different directions. So what we did was we rotated the body. We are going to do something similar, except we cannot rotate it any way we like. So fiber reinforced materials, and we are going to assume that fibers are parallel to each other, and for our purpose basically if fibers are not parallel to each other, then you are considering a very small volume. Even though I am showing you big picture, but assume that it's a blown up view of say 1 millimeter by 1 millimeter by 1 millimeter body. So this is the fiber direction in the reference configuration, A0. So now if the hypothesis is, the assumption is that if you rotate the body about A0 is the axis of rotation, then material properties should not change. Similar thing holds for a piezoelectric material. I think some of you might be interested in smart structures or smart materials. So in smart materials, instead of saying this A0 is a fiber, you say A0 is the direction of polarization. So if you have a piezoelectric material, we say A0 is the direction of polarization, and then material response is transversely isotropic. So any rotation about A0 cannot be detected by experiments or by our mechanical experiments. So that is the hypothesis. And liquid crystals, again you have a direction vector. Some of these TVs, color TVs, they have liquid crystal display. So again, depending upon the direction of that A0, that polarization vector, you can see a different color. And there are like our muscles. If you wish to simulate our muscles, they also are tissues with muscles in them, then again same thing. So A0 is the direction of the muscle. This is an assumption now that the material response is transversely isotropic. And if you put two families of fibers perpendicular to each other, then it will become orthotropic. So then it will be a different story. So whatever we will do for a transversely isotropic will not apply to an orthotropic material. So the reason I am saying will not, because then you might get the impression that we are covering two families of fibers. No, we are not. It's only one family of fibers, and that's parallel to each other. I think if you those of you who are more interested in this fiber reinforced stuff, so you may want to, I think Spencer's book has a good discussion. So A.J.M. Spencer, unfortunately he passed away a few years ago, but read his book or papers. And then I think you are smiling. Why?
I used it during my postdoc.
Good. So you know more about it than I do.
No, but it was in the context of plant cell walls.
Same thing. Plants are similar thing happens if you have a plant, because you are still modeling it as a transversely isotropic material. So instead of the muscle, that vertical axis in the plant through which the feed is going, I guess, and if you cut the trunk, you see circles. Each circle, I think, represents 1 year of age. So you can guess or you can estimate the age of the tree by cutting the trunk and looking at the number of circles. Of course, if you cut wood from a tree, there are defects. You see some knots sometimes. They are not being considered in our work. Same thing like if I got a cut on my leg, that cut is not being modeled. What we are simulating is basically a newborn child. Everything is perfect. Okay, so we showed yesterday that phi, the free energy, because of the material objectivity. Material objectivity means that you take the current configuration and you superimpose a rigid body motion on the current configuration. It has nothing to do with the reference configuration. So, instead of having phi energy depending upon F deformation gradient, it can only depend upon either U or C or E. Which one will you prefer now? So, E. Okay. So, say E. So, E is 1/2 C minus identity. So, it is the same thing as saying it depends upon C. And now it will also be a function of A0, this rotation matrix. Now, if we say that this thing should be invariant, should not change if I rotate the reference configuration about A0 as the axis of rotation, then this thing should equal phi H E H transpose H A0 for every H, of course, it's orthogonal. So, H inverse equals H transpose, and H A0 equals alpha times A0. Actually, alpha is 1, eigenvalue is 1. This last statement means A0 is the axis of rotation of H. So, yesterday we did not put this condition because we talked about isotropic materials. So, A0 could have been any vector, but today because we have a fiber reinforced material, so A0 is the direction along which the fibers are oriented. So, we already used objectivity because objectivity reduced dependence from F to dependence upon E. Okay. So, now if we exploit this, then this phi really can be a function of invariants of E, which are related to the invariants of C. So, even though I said that we can use any one, my algebra will be simplified if I use C when I am going to derive the expression for the Cauchy stress, but nothing will change, seriously. It is just because I will have to do when I differentiate E with respect to F or C with respect to F, the derivative of this is going to be 0. So, that is why it really won't matter. So, it's first invariant of C, second invariant of C, third invariant of C. Now, the direction A0 has not come into picture yet, right, and that is the case for an isotropic material also. Now, the direction will come into picture. So, this is A0 C A0. So, what I mean by this one is it is A0 L C L M A0 M. 0 is not an index, 0 is just that it is in the reference configuration. So, that is this thing is that one. So, C operates upon A0 will give you a vector. C operating upon A0 will give us a vector, then you take the dot product of that with A0. And I am not done yet. So, there is one more term. So, that is A0 C square A0. Now, why not C cube and C4 and C5th and C6th? Obviously, that question should come up, right? Why did I stop at C square? Not only I, it is a mathematical theorem. It's nothing to do with my preferences. So, the reason is the following. The reason is that this identity holds. We have a 3 by 3 matrix. So, C cube minus first invariant C square plus second invariant C minus third invariant times identity is 0. Okay. No matter which 3 by 3 matrix you take, this is Hamilton-Cayley theorem. And excuse me, when we find eigenvalues, when we find eigenvalues, we have lambda cube minus IC lambda square. So it's basically coming from that. So this is Hamilton-Cayley theorem. So if I have C cube, I can express C cube in terms of C square, C and identity. So if I had written A0 C cube A0, then I could use Hamilton-Cayley theorem or Cayley-Hamilton theorem and express A0 C cube A0 in terms of that, because we did not say how they depend. So that's why we only go up to C square and nothing, not more. So we can, if you like, we can say this is first invariant, second invariant, third invariant, fourth invariant and fifth invariant. And if you have a mutually perpendicular fibers, then you get more invariants, because that direction will also come into picture. Okay, so the theory, I think as you were asking me, the theory does not predict the form of this function, free energy. That's all where the theory can go, only this far. How, like phi depends upon these 5 invariants, you have to do experiments. So that's different for different materials. So if you have different fibers in the same epoxy, phi will be different. There is no viscous effect being considered. There will be no heat produced if you deform this material cyclically. You can consider the temperature dependence of material properties. Like you can say, like we had yesterday, phi depending upon E and theta. So that part is allowed, that if you do experiments at different temperatures, the Young's modulus or the shear modulus or the bulk modulus will be a function of temperature. But now generally speaking, temperature, we use these kind of materials at a constant temperature. Actually, I misspoke. There is some, yes, I spoke, I was wrong. And there is some heat produced even if you use an elastic material. If you use coupled thermoelasticity, yes, there is heat produced, even in linear coupled thermoelasticity. But 99% of the literature uses uncoupled thermoelasticity or one-way coupled thermoelasticity, which means you solve the heat equation without considering that the heat produced because of the volume change, dilatational part. So there is some heat produced. I was wrong. And,
What is the physical basis for that?
physical basis is because heat conduction is an irreversible process. And now you are coupling heat conduction with elastic deformations. So it's the coefficient, it's the thermomechanical coupling factor comes into picture, like in piezoelectricity is the thermoelectrical coupling factor comes into picture. So if you linearize equation, you see that. And I told you during coffee break, no, but it's not enough to see what you get in tires, say, because the temperature rise due to thermomechanical coupling will not come out to be significant enough to see, oh, okay, in my tires, if I have been driving for say 2 hours or 3 hours, the tires do get hot, and therefore material properties change. I know you are not happy with it, but I will show you later on.
I think it's just equivalent to the Onsager reciprocal just from one set you have.
You know, I mean, Trussell did not believe in Onsager's irreversibility or symmetry part. So that's, I mean, there are many reasons why people don't like Trussell or did not like him. So one of them is that he spoke his mind, and people did not like that. So if you read his book, it says that Onsager's, like the symmetry of K follows from Onsager's relations, something like that. He says all bogus. Maybe he did not use the word bogus, but something equivalent. He probably used even a stronger word. So, and as we saw in our case, the symmetric part of conductivity tensor has to be positive definite. But the theory, Coleman-Knowles approach of using Clausius-Doom inequality did not give us that thermal conductivity tensor must be positive. All it said was that the must be symmetric. All it said was that the symmetric part must be positive definite. It does not say that thermal conductivity tensor must be symmetric. So, I mean, the math did not give us. If we can of course assume it is symmetric.
I think it was negative definite.
Okay, well,
Yeah.
negative. Actually, thermal conductivity tensor is positive definite, but Q, we put Q equal to minus K times temperature gradient. So, I mean, if it is positive definite, I can change the sign and make it negative definite and vice versa. So that's not a serious issue, right? Okay. So I think for us, we are to save some writing, we are not going to do that, because then I have to expand in terms of theta also, and so I'm not going to do that. Okay, so what is then TIL? So that's delta, well, so we have delta phi over delta IC times IC over FIL. And now I have not expanded phi in terms of Taylor series. So this is still a function of 5 invariants. I mean, I could expand it in terms of Taylor series, but I have not done that here. So this is a function of 5 invariants. And same thing about the second one. And about the third one. And let's write this as I4 and write this as I5. Instead of writing A0 C A0, so this is delta phi over delta I4 and then I4 with respect to FIL plus delta phi over delta I5 over FIL. And now if you see the literature, many people, they have expressed the free energy either by considering only I4 or I5. So they write a special form for the free energy in which they have, I think you are not happy.
These are W's, right? Actually.
I'm sorry?
These phi's are actually W's, right?
Yeah, it's the same. I think yesterday you are right. I had written rho 0 phi equal to W. So I should put rho 0 in front here. You are right. Because that's the expression we had, that T tilde equals rho 0 times those derivatives. Sorry, I forgot that rho 0. Okay. So Now, if we simplify this, the simplification of this part is similar to what we do for a elastic material, except the coefficients are now functions of 5 invariants. So, if you don't mind, I am not going to do that. So, these ones you can see the A0 coming into picture. Now, if we write Cauchy stress tensor Tij, so that's 1 over j T tilde IL F JL, and I think this is correct. So, if you write Cauchy stress tensor, so it's 1 over j times all that stuff, and so this will be like rho 0 over j times the first 3 terms will give us something like F0 times, I have indices, so delta Ij plus F1 times Bij plus F minus 1 times B inverse Ij the first 3 terms. Actually, I have skipped quite a few steps. So, in the interest of saving time, I have skipped those steps. But if you want me to, I can differentiate this with respect to F, and then show you that if you multiply with this, you will get B. And same thing here, you will get either B square or B inverse because of the Hamilton-Cayley theorem. And this one will give us identity, because if you differentiate Jacobian J with respect to F, you get F inverse. So, if you differentiate, like say this one 3C FIL, 3C is determinant of F square, because C is F transpose F. When you take determinant of F transpose is same as determinant of F, so you get J square. So, if you differentiate, you will get twice J, and then J with respect to F, and if you evaluate this, so this is J F inverse Li, and since you have a F here, so that will give us identity. So, all the terms are there, like F0, and this is just a F minus 1 is just a notation, is similar to F1, except saying that this is the coefficient or factor multiplying B inverse. It's like C1, C2. Instead of writing C2, I am writing C minus 1. Okay? Because the more interesting part is the other two. But the difference between an elastic material and this fiber reinforced material is this F0, F1 and F minus 1, they depend upon all these 5 invariants. And if we do linearization like we did yesterday, then you will see things simplify some, of course. Okay, now let's look at the other two. So, this one differentiate I4 with respect to F. So, I4 is A0 L C, no, I should not write L anymore because I have L here. So, it's C0 M CMN A0N, which is A0M FIM. I is not a good choice, so JM JN A0N. that's I4. Because I have to differentiate it, so that's why I wrote it like that. So if I differentiate it now, so delta I4 over delta FIL, so I will get A0M differentiate this, you get delta Ij, delta Mn and Fjn A0n. There are two F's, so you will get two terms, the chain rule of calculus. So the second one will be A0m Fjm delta Ji delta Nl A0n. Is it okay? Now, so let's look at this is Ij. So this will become I, Nn will become M. Right? Because this J and J is summed, so J is replaced by I, M and N is summed, so N is replaced by M. So what is this thing equal to? So it is FIM A0M. Very good. So it's a deformed, it's the vector into which A0 is deformed. On the very first day, we said P prime Q prime equals F PQ. So this is PQ. This is F operating upon PQ. So we get the deformed vector, not of unit length, no. It's if A0 is of unit length, this one is not necessarily of unit length. So let's write, say, AI equals FIM A0M. Is it okay? So that takes care of some of the terms. There is A0n left here. Of course, I have a mistake. That's why I'm getting in trouble, because I differentiated wrong. I have n, n, n. It's too many n's. 3 n's, which is wrong. Sorry, let me redo it. So it's A0M JM, so that's Ij ML FJN A0N. On this side is okay. MM NN. Yeah. Sorry, I had goofed because we had too many n's. Okay, now we are in better shape. So this J becomes I. So this is gone. This A0M, this is delta ML. So that means this becomes L. Right? So now if you allow me, I can get rid of this because we have used it. And we have used this. So what is this one? Fjn A0n Aj. So let me write here Aj. So that is this part. See this FGL, that's going to operate on this. Right? So that will give me AI. No, J. So this gave me AI. FGL operating upon this one will give me AJ. And now we look at the next term. Is it okay? So the next term we have J and J, so that becomes I, and L and L. L and L, so this becomes L. Oh, yes. Sorry, N and N, so this becomes L. So we have used this one and that one. Is it okay? So I can erase this. Now FIM A0M. So that gives me AI, little AI, A0L, FJL, so AJ. And of course, both of these terms are symmetric, like AI, AJ, symmetric in I and J. I did not play any tricks. So I can just write here twice, and so we get AI, AJ plus I5. Now roughly speaking, I5 has C square in it, right? So you will get 2C times derivative of C with respect to F, roughly speaking, right? So if you do the algebra, then what you will get is probably something like this: I5 AI B J K A K plus A J B I K A K. So it's symmetric in I and J. Like I skipped the algebra part. Okay, I did not differentiate them, but most likely you will get something like this. Again, it is symmetric in I and J. That's the whole idea. This B comes because we have C square here. So when you differentiate, you will get C times derivative of C with respect to F, but there's an F here also. So that's why you pick up a B rather than without any term. So this will show up and this will show up. So now, so this is the general constitutive equation for a transversely isotropic material. But the difficulty here is that we have F0 to find, F1, F minus 1, this factor. Oh, there is probably a factor of 4 here, but that doesn't matter. This number 4 doesn't matter though. Maybe it's a 2. Anyway, it doesn't matter, right? Whether it's 4 or 2, it's insignificant because we have to find that quantity. So it's a tremendous task. So what people do, most of the time we use Taylor series expansion like we did yesterday. So if you do Taylor series expansion, then you can as well work from here rather than using the invariants, or you can work from here and use invariants. It's up to you. So one possibility is that you can say this is a constant, that's a constant, this one is a constant, like we did for monorevelant material. This is a constant and that's a constant. So you have 5 constants, and you can absorb like rho 0 over j, because we have rho j equal to rho 0, right? So rho 0 over j is rho, or you can say j, this j here is square root of third invariant, and you can say, okay, I will absorb this invariant in F0, absorb this in F1, absorb that in F minus 1, and in this one and in that one. So you don't have to worry about the term that's outside. And rho 0 is mass density in the reference configuration, which you know. So in principle, you could potentially absorb this term which is outside into these, each one of these 5. So we still have to find 5 constants, which is, I cannot give you like Rivelant plot because I don't know it even that this will fit into a Rivelant plot. Actually, obviously it won't fit because there are 5 constants. And Rivelant plot, we were lucky that we could find 2 constants from one plot. So here, unfortunately, we have to do more work. I mean, transversely isotropic materials have 5 constants. So we have to find the values of these 5 experimentally. There is no easy way out. Any questions you want to ask about this? And if it were orthotropic, like 2 families of fibers perpendicular to each other, then there will be 9 constants. Please speak up if there is any question. Yes, you want to ask? No? Okay, so we have maybe a few minutes. So let me take another special case, because you might, so we have not talked about fluid so far. So let's take a, I'm going to raise this if you don't have any questions. Okay, so what about this fluid now, this water? What kind of symmetry group does it have? See, yesterday we talked about isotropic materials. For an isotropic material, you can take the reference configuration and rotate it by any angle, any orthogonal matrix. What about this one? Let's assume that our reference configuration is now water. So what kind of changes I can make to it so that the response cannot be detected? So to give you an idea, let's say the bottle is this way. If you test it one way, what if I do this way and you test it? Will you see any difference? No. Good. What about this way? No. So long as you do not change the density of water, no test can detect it. Whether you have bottle like this way, that way. So if you rotate the reference configuration by any matrix, including orthogonal, that do not change the mass density, we are in good shape. So what that means is then that F, that this phi, I will need this. So let me keep that part. So this phi, which is a function of F, for a mechanical problem, forget about temperature. So it's a function of F for an elastic material. And now let's assume this is water. This is, we are assuming it is inviscid, not non-viscous. Because if it is viscous, then I have to consider F dot also, which I am not considering. So we are considering perfect fluids like gases or water. It makes no difference. So this should be same if I first rotate it, turn it, whatever, so long as I don't change the mass density, which means determinant of H should be 1, plus minus 1. Or so this equation should be satisfied for all matrices H that have determinant equal to 1. They can be non-orthogonal. There are non-orthogonal matrices, which means H1, H inverse not equal to H transpose, but have determinant 1. Now this equation holds if and only if phi depends upon J, determinant of F. Otherwise, you cannot have that equation satisfied. So that holds if and only if phi is a function of J, determinant of F, which is J, or square root of 3c. Now if you take this one and find Cauchy stress Tij, which is 1 over j T tilde, which is 1 over j delta phi rho 0, delta phi over delta FIL, FJL, so which is 1 over rho 0, delta phi over delta j, and delta j over delta FIL, FJL, but this quantity is J F inverse Li. If you differentiate J with respect to F, you get J F inverse Li. And now, so this thing, oh, what did I do? 1 over J here. So rho 0 over J is rho, because we set rho J equal to rho 0, balance of mass, and delta phi over delta J, and this one is J F inverse times this is delta Ij. And this J, I could also write it as rho 0 over rho, because J is same thing as rho 0 over rho, which is same thing as saying it's a different function of rho, because rho 0 is fixed. If it's a function of 1 over j, it's function of like if it's a function of rho 0 over rho, so it's a different function of rho. So here, instead of differentiating with respect to j, I could differentiate with respect to rho. So what we get then is that this is some function of rho delta Ij. and this minus sign is conventional. So this minus sign, this quantity is this quantity. Minus is conventional. I mean, this is a so in our theory then, an inviscid fluid is covered. When we have studied the constitutive relation for an inviscid fluid, not incompressible, inviscid fluid, but this one is compressible. Compressible means mass density can change. So what will happen if the fluid is incompressible? Is my statement making sense? See, we did this for a compressible fluid. Now let's assume our fluid is incompressible. Yes, pardon me? J equal to 1, but how will my Tij change? See, this is my stress strain law now. Tij is equal to minus P of rho delta Ij. So this is good for an for a compressible inviscid fluid, non-viscous compressible fluid. Now we have a non-viscous incompressible fluid.
It is not no more a function of rho because rho is not zero.
So yes, so if it is incompressible, then Tij will be minus P delta Ij. So what is this P a function of? How do I find P? How many of you are in fluid mechanics?
So we say that in for special cases we can say that at a depth h it is rho g h square.
Pardon me?
You can find it from boundary condition.
Good. And solving the equilibrium equations. We did in the morning. We just solved that membrane problem. There we had P. We assume material is incompressible, right? So this P is a function of x, y, z, and time. If it's a time-dependent problem, otherwise it's a function of x, y, and z. And it is to be determined by solving the equilibrium equations and satisfying the boundary conditions. It is not.
What is said, I mean, would be from a boundary condition, I mean boundary value problem.
He said that.
No. So what he said that it varies linearly with the depth.
No. He said rho g h. Yeah, special case. Yeah, he said rho g h. So in that case, fluid is not moving. Yes. Well, maybe I guess one could interpret that way, but he said boundary conditions. So it's really a solution of equilibrium equations and boundary conditions. See, in rho g h, what about x and y? H is supposing the height, z coordinate, but it can be a function of x and y too, if the fluid is flowing. I'm just being but anyway, you cannot find the only way you can find is by solving equilibrium or solving equations of motion and satisfying initial and boundary conditions. So this ideal fluid is a special case of an elastic material for which the free energy or the stored energy is a function of mass density only. How it depends upon the mass density, of course, depends upon whether you are talking about argon or air or oxygen or hydrogen or water. Because all of you, we learned PV equal to R theta, right? In our undergraduate courses. Theta is the temperature here. So this volume is 1 over rho. So P is equal to R theta rho. And so that's a special case of what we did. This is like here says P is a function of rho. This is a special function r theta rho. So what I'm trying to say is that we have covered perfect fluid. This is because this dependence is well, roughly speaking linear. Actually in this case it is linear, but if the process is adiabatic, then you say PV raised to the power gamma is constant. So then it will no longer be P equal to rho here, but it will be rho raised to the power 1 over gamma, and then it will be nonlinear. But we will say then it's an adiabatic process, and where gamma is the ratio of specific heats. We did not prove that, but that's a constitutive equation that you get. Again, it boils down to the same thing. We cannot find the specific forms by using this theory. You have to do experiments, and that PV raised to the power gamma equal to constant comes from experimental data rather than the theory part. And you find gamma as a ratio of specific heats from experimental data. Okay, so this gives you a little bit idea of the transversely isotropic material. So the stress tensor does involve fiber direction in the deformed state. Now in Spencer, he has also talked about what if the fibers are inextensible. Say in addition to the whole thing being incompressible, what if we assume that the fibers are inextensible, then the things will change. Then you need one more Lagrange multiplier. Okay, so we will see what you wish to cover in the afternoon. So we will meet at 2 o'clock. Okay, thank you.